In this session, we talk about the concept of particle size and shape. Now, to start with, why are you concerned about particle size and shape? Mostly we'll be talking about process equipment, meaning equipment used in the process industry. And in the process industry, both solids and fluids are encountered, meaning we need to deal with solids as well as fluids. Now, the solids that we'll be talking about are mainly small particles and particles in mass. So we need to define the characteristics of mass of particles. Now, what are the properties we should look at? If you're talking about fluid, we typically look at the properties density and viscosity. Now, why for fluids the density and viscosity, these two properties are so important? One of the reasons is that we need to transport fluids, and the equipment design as well as the rate of transport all will depend on these two properties, density and viscosity. Now, fluid does not have shape, so that shapelessness really differentiates between fluid and solid. Now, due to the shape of solid particles, the transportation of solid is different from that of fluid. Now, in this regard, what properties are important for the transportation of solid? The two properties that defines the transportation characteristic are the shape and size. Depending on the shape and size of fluids, the transportation will depend. Now, these are not the only properties that we are interested in. There are other properties. For example, density is important for the case of fluidization. Hardness, toughness, or stickiness, these are important for particle size reduction. For heat transfer, the thermal conductivity of solids will be important. Now, we said that we need to define the size and shape of particle. Now, when you say size, what do you really mean? Often we call big and small to describe size, but what is big for a processing facility may be really small for mining operations. And what is small for a processing facility may be too big for a nano operation. Or within the process industry, what is small for catalysis may be too big for a membrane operation. So we need to define size based on the use of the particle and the context and the equipment under consideration. Here is a simple description. Although these particles are involved mainly in the agricultural field, so the clay, silt, sand, gravel, so those sizes vary between around less than a micron, that's a micrometer, up to maybe some centimeters. The aerosol reactor involves something really very small particles. The fluidized bed will involve something in the range of maybe 10 microns all the way to around a millimeter or so. So depending on the applications, we'll encounter different sizes of particles. Also, depending on the size, how to measure the size, those technology will be different. So we need to consider the size of the particle for the relevant application, also the measurement techniques that's used to measure those sizes. In this figure, the sizes are described in terms of micron, centimeter, millimeter, or meter. However, what does this size mean? What are you talking about in this case when you say size? If you say it's a diameter, then typically we're considering spherical particles. For say if it's a cube, we can say the cube with one dimension having certain length. In those two examples that we gave, one is a sphere or another is the cube, those are what is called these regular shaped particles. Now, for regular shaped particles, there is a characteristic dimension, meaning you can describe a sphere by saying its radius. You can describe a cube by mentioning the length of its one side. And if those dimensions are given, you can find out the other characteristics. For example, if you know the diameter of a sphere, if it's d, then its volume is pi over 6 d cube and its surface area is pi d squared. Now, in real life, most particles are really irregular in shape, meaning they are not of a regular shape. If you look at even some fruits, say apple, it's not spherical. If we look at some other things, for example, just look at the human head. It does not have a regular shape. The grains you look at or other materials around and the minerals and rocks, you will notice that mostly none of those have a regular shape. So, as we said, if the particle is of a regular shape, we can define it by particular dimension. Now, what about the case when the particle is not of a regular shape? Meaning that how do we really define the size of an apple? How do we define the size of a human head? So, that's the main point here, that how to define the size of irregular shaped particles. Now, the fundamental problem here is how to define a three-dimensional irregular shaped particles by one dimension. If I ask you, what is the shape of an apple? Yeah, I'm talking about the fruit, not the computer. So, in that case, before defining the size, we need to define another parameter to describe its shape. So, shape, it's needed to be described first before describing the size of a particle. Now, how to describe the shape? Among the regular shaped particles, the sphere has some unique properties. A sphere is totally symmetric, meaning that you can see the sphere from every direction, it will look the same. That's unique to the sphere compared to any other regular or irregular shaped particles. That's why you can really define a sphere using only one dimension, which is its diameter. Another important property which is important for the process industry is that the sphere has the smallest surface area to volume ratio. Meaning that if you build any regular or irregular shaped particle having the same volume, among those, the sphere will have the minimum surface area. That's the reason you see that when you look at some LNG carriers, you see that its top part is designed as a sphere. Why is that? Because LNG carriers carry liquefied natural gas, which is LNG, at a very low temperature, and they need to minimize the heat transfer. And to minimize the heat transfer, they need to minimize the area. And that's why they build the container, especially the top part, like a sphere. Now, because of these two properties, one is its complete symmetry, another its surface area to volume ratio, the sphere is taken as a standard to define the shape of other particles. Other particles are compared with a sphere in terms of one particular property, which is called this sphericity. Now, what is sphericity? The fundamental definition of sphericity is that it's defined as the surface area of a sphere having the same volume divided by the surface area of the particle. Again, the sphericity is defined as the surface area of a sphere with the same volume as the particle divided by the surface area of the particle. Now, if we define Vp as the volume of the particle and V SPH as the volume of the sphere, then we have pi s equals S over V for the sphere divided by S over V for the particle. Now you see, simply because these two, we said that the particle and sphere has the same volume, so those two are same, so we can divide the numerator and denominator by this. Now for a sphere, we see that the surface area can be defined as pi d squared and the volume can be defined as pi over 6 d cube, where this dSPH is the diameter of the sphere having the equal volume of the particle. Simply using this, we see that for the sphere, the surface area to volume ratio is 6 over the diameter of the sphere. So this gives us the sphericity of a particle is equal to 6 over the diameter of the sphere having the same volume as the particle over the surface area to volume ratio of the particle itself. Now for irregular shaped particles, we define something called the equivalent diameter. The equivalent diameter of a particle is defined as the diameter of a sphere having the same volume as that of the particle. So you see here, the diameter of the volume is equal to the equivalent diameter of the particle. So by replacing this, we get phi s equals 6 over dp by sp over bp, meaning the 6 over the diameter of the particle divided by the ratio of surface area of the particle to its volume. Now the sphericity of a particle with a particular shape will be independent of its size, meaning that sphericity of all the cubes will be the same. If you take some apples with different sizes but having the same shape, you will have the same sphericity. A few notes on the equivalent diameter. So as I said that the equivalent diameter is defined as the diameter of a sphere having the same volume as that of the particle. However, in some cases the equivalent diameter is defined arbitrarily, meaning that sometimes the equivalent diameter of a cube is defined as the length of one side, and also sometimes it's called the nominal diameter. Sometimes the second largest dimension is taken as the equivalent diameter. Say for a cylinder, the diameter can be taken as the equivalent diameter. Now for irregular materials, often the equivalent diameter is determined based on the screen size. We'll see what does it mean when you look at detailed about the screen analysis. We have defined the term sphericity. Now what is the use of sphericity? If we need to know the surface area and the volume to estimate sphericity, then what's its use? Now in reality, the sphericity is used to calculate other properties. Sphericity independent of the particle size, and if the two particles have the same shape, their sphericity will be the same. So in reality, you will see that many particles may have the same shape. For example, if you take many different apples of different sizes, you see that their shape may be almost the same, meaning their sphericity will be quite the same. The same thing happens for many mineral deposits, or maybe some crystal formed in a crystallization process, that the particles may not be of a regular shape. However, their shape will be almost the same, although their sizes may be different. Minerals can deposit over a long time, and the time of deposition may vary, and depending on that, the size of the deposits may be different. However, their shape may be the same, and that happens for many minerals, and for that case we have the same sphericity. So if you know the sphericity of a particular mineral, you can calculate its other property by using it when you are considering the same mineral with different sizes. The same can happen with the crystallization process. So if you know the shape of a crystal, you know its sphericity, and you can use it to calculate other properties of a bulk set of crystals having different sizes. So here is some example of materials and their sphericity. Say here in this example, you see that the sphericity of cubes, short cylinders are 1. This is because the equivalent diameter is defined in the arbitrary way, meaning that for cubes the equivalent diameter is defined as it's the length of one side. For short cylinder with length equals the diameter, the equivalent diameter is defined as its diameter. So that's why it's 1. We see that if you take the other definition, meaning if you define the equivalent diameter as the diameter of a sphere having the equal volume, we see that for cubes and cylinders, different numbers will be obtained. So for the bowl saddle, which is one of the filling used in adsorption or distillation towers, its equivalent diameter is around 0.3, Ottawa sand almost 1, rounded sand 8.83, mica flex 0.28, and glass 0.65. You see here that all of these numbers are equal to or less than 1. This is because, as I said, that sphericity for a sphere, the surface area to volume ratio is the minimum. of any shape of particle. So that's why this P over Vp is minimum for a sphere, and that's why the sphericity is the maximum for a sphere, which is 1. So no other particles will have sphericity more than 1. Another term we need to use, which is called this volume shape factor. So you know that for any particle, the volume is proportional to the cube of its diameter. Now we will use the term diameter to really mean equivalent diameter, meaning we're not talking about all regular shaped particles. Now if we replace this proportional sign by an equal sign, you can say that Vp equals a dp cube. Here A is called this volume shape factor, meaning the number that you need to multiply dp cube to get the volume is called the volume shape factor. So you know that for a sphere it's pi over 6, and for a cube it's 1. So the volume shape factor is independent of the size, meaning for any cube it's 1, and for any sphere, independent of what's its size, its volume shape factor remains the same.